and energy estimates for the boundary layer problem. And so this is work that's built up on something that's known in the community as the Kato criterion for the vanishing viscosity problem. Okay? All right, so I'd like to acknowledge my collaborators in this, and so since I'm going to be mentioning several different works, there are several different collaborators. They're not all in the same papers. So Drago Shiftimie from the University of Lyon in France, Tim Kelleher from University of California, Riverside, Milton Lopes Filho from UFRJ, Anna Matsukato, Penn State University, Michael Taylor, University of North Carolina, Idris Titi, it's written Weizmann Institute at UC Irvine, but actually has now moved to Texas A&M. And Aibin Zhang was a postdoc from Yushin University who spent 1.5 years at UFRJ. Okay, so first of all, let me set up the problem. The problem that I'm going to talk about is the vanishing viscosity limit. So I'm going to consider incompressible Navier-Stokes equations in a bounded domain, which I'll assume smooth. And by smooth, I mean as smooth as necessary, so I won't go into details. Here's the, just to set up notation, fixed notation. I have the Navier-Stokes equations, ut plus u dot grad applied to u equals minus gradient of t plus nu times the Laplacian of u. That's understood component-wise. Divergence of u is 0 is an indication of incompressibility, and boundary conditions on the boundary. Okay, so we'll discuss this later, and initial conditions. Okay, when the viscosity is 0, these are known as the incompressible Euler equations, and in that case, we take the non-penetration boundary conditions, which means the flow simply slips along the boundary, u dot n is 0. Okay, and if nu is positive, we take the no-slip boundary conditions, which means u is attached, the particles are attached to the boundary. Okay. Our problem is to understand the vanishing viscosity limit, and I want to make things simple, so I'm going to go 2D, because in 2D we have a lot of estimates, and so there's a lot of analysis that can be done in this case. Okay, so I'm thinking about two-dimensional flow in a bounded, simply connected, smooth domain, connected and simply connected smooth domain in R2. Okay. Vorticity is an important thing in this mess, so I'm going to take initial vorticity, which is just smooth, compactly supported, just a bump function, and I will take the associated Biot-Savart law, so the velocity initially is the grad perp of the Dirichlet-Laplacian inverse of this initial vorticity. And so by the way, the initial vorticity is just a scalar. I'm identifying the three-dimensional curl with the last component of the curl vector, because the vorticity is just 0, 0, comma, omega. Okay? All right. So u nu represents the weak solution of the Navier-Stokes equations with viscosity nu. And the question is, can I find any subsequence, nu k, converging to 0, such that the corresponding Navier-Stokes velocities converge strongly in L infinity in time and L2 in space to something, anything, okay? In particular, will this something be a weak solution in any sense to the incompressible 2D Euler equations with initial velocity u naught? Okay, an observation that's relevant in this story is that you have uniqueness for Navier-Stokes in this setting. Weak solutions are unique in 2D. However, you do not have uniqueness for the Euler equations in this setting. Okay, it's too general. Even with smooth data, you have no uniqueness for Euler. Now we know the existence of wild solutions, even with 0 initial data, okay, for Euler. Okay, so what I want to probe in this lecture is, what the heck is the difficulty in this problem? Why is it a difficult problem? Okay, and so one possibility is that one sort of obvious possibility is that the issue is in the mismatched boundary conditions. So in Navier-Stokes, you have u equals 0 on the boundary, so you have two boundary conditions, whereas for Euler, you only take the normal component to be 0. Okay? And so let's look at this a little bit. Assume for a moment that you solve the Euler equations with some initial velocity, which happened to be 0 on the boundary, happen to have the same boundary condition as Navier-Stokes, and just assume for a second that the Euler equations preserves this. Okay, you've chosen a very special initial data, very special situation, where the initial velocity for the Euler equations is 0 on the boundary, and this is maintained throughout the flow. Okay, I'll discuss situations in which this actually does happen later. All right, let's do some very simple-minded energy estimates. Okay, so you look at the difference, U Navier-Stokes minus U Euler. You look at the equation for the difference, here it is. Okay, you multiply by W at integrated space, and you get this equation here. Okay, so you get ddt of the L2 norm squared of the difference over 2 is equal to the nonlinear term plus a linear term with a Laplacian. Okay, since the difference is 0 on the boundary, you can actually integrate by parts the linear term, the Laplacian, okay, and you get this object here. And so you substituted this in there, and then before I go further, okay, I've got gradient of U nu, so now I'm going to split this gradient of W in 2 parts. Okay, one which is gradient of, gradient of UE, the other one is, where am I? Oh, sorry. Okay, let me use this. Okay, so, is this here? Yes. Okay, so here I'm going to take this gradient of U Euler, assuming that I'm going to have some kind of nice solution of the Euler equations, which I can actually play with, and it's bounded, and so I can take this guy here and bound this at L infinity. I get the L2 norm squared of W, and then I have this term here to play with. Okay, and I can split this in 2. So here's the term from the nonlinearity, and then I can split this into 2 nu times gradient of W minus nu times gradient of W times gradient of UE. Gradient of UE is under control. Okay, so I throw this term away, and using some kind of Young's inequality, and so I've got gradient of UE L2 squared times something small. And I'm done. Using Rodwell's lemma, the L2 norm of the difference squared goes to 0 when viscosity goes to 0. So in this situation, it's easy to prove that the Navier-Stokes equation's solutions converge to Euler. Okay? Now, let me discuss for just a second here some situations in which the Euler solution does vanish on the boundary throughout time, and most of them are just, in fact, I think all of them are just steady solutions. Okay, so if you take some radially symmetric vorticity in a disk, okay, with vanishing total mass, then you get such a situation. And you can actually superimpose 2 of these, okay, and because basically, if you have radially symmetric vorticity with vanishing mass in a disk, that will generate a velocity field which is identically 0 outside of the supportive vorticity, okay? And so you can superimpose these objects in any kind of bounded domain, each one radially symmetric with respect to its center, okay? And this generates something which is steady for Euler. It's not steady for Navier-Stokes, but it's steady for Euler, okay? And it's 0 on the boundary. The velocity is 0 on the boundary, okay? Now, this seems very simple-minded. However, there's a paper which is relatively recent, 2002, by Jerry Bowen and Jahong Wu, in which they go to great lengths, in fact, to prove exactly this. Sorry about that. Okay. And so together with Milton Lopes and HJN, we also worked on something similar in which we were discussing the most irregular, most singular possible vorticity for which this works. Okay. Now, what about the general case? So the general case has been addressed by the Kato criterion. Okay. This appeared in a very short and sort of obscure note by Kato, which was published in these UC Berkeley seminars, PDE seminars, and it's known in the community, but I'm not sure how widespread it is. Okay, so I'm going to make, again, my life simple. I'm taking UC infinity, U naught C infinity, tangent to the boundary. In other words, no non-penetration. You use the unique, now weak solution of the incompressible Navier-Stokes equations. I'm allowing for an initial boundary, an initial layer. Okay, I don't care whether the initial velocity satisfies a no-slip or not. Okay, and UE is a unique smooth solution. So among the class of smooth solutions, uniqueness is known for Euler. Right, and in this short paper by Kato in 1984, he proved the following criterion. The vanishing viscosity limit holds in L infinity in time, L2 in space, if and only if the dissipation rate, okay, viscosity integral in time times the integral of the gradient of u nu squared dx ds. This is integrated in a thin region near the boundary of thickness order nu. Okay, if and only if this is the dissipation rate. Okay, so if that dissipation rate goes to 0 in a thin region near the boundary of order exactly nu. Note that this is nu, this is not square root of nu, so this is not the Prandtl boundary layer, this is the Kato boundary layer. Okay? All right. What's interesting is the equivalence. This is an if and only if condition. Okay? So what we ask here is, what is special about this thickness? And in order to understand this, let's examine the proof. Okay, so I will give you the proof of the Kato criterion. One direction is very easy. You just start from the energy inequality. So you have, for Navier-Stokes, you have the L2 norm squared plus the time dissipation 2 nu times gradient of u and L2 squared is bounded by the initial L2 norm of squared. Okay? Therefore, you look at the dissipation rate 2 nu integral in time of gradient of u squared, and it's bounded by u naught L2 squared minus u nu L2 squared at time t. If you have the vanishing viscosity holding, okay, which means convergence, then your right-hand side converges to 0, your left-hand side is greater or equal to 0, and therefore, you got it, okay? So that gives you one side. It's very easy. Note that the dissipation in the easy direction happens in the whole domain. Okay, not only near the boundary, but in the whole domain. Okay? Okay, now here's the heart of the matter. Okay, the converse. Okay, so here's where we need a boundary corrector. So I'll do it in 2D for simplicity. Things get a lot more explicit and simple here. I'll choose a smooth cutoff near the boundary phi, which is one on the bound in the neighborhood of the boundary, and I'm just going to rescale this. Okay, I look at the stream function for the Euler solution. My boundary corrector is just going to be a cutoff of the stream function, and I take the grad perp of that to make it divergence free. Okay, so this is my boundary corrector function. The main advantage is that this thing is 0. I'm sorry, that this thing matches the, what is it? Sorry. This matches the Euler flow on the boundary, okay? So if I take the difference with the Euler velocity, that's 0. So this is something which is supported near the boundary in a region of size delta, near the boundary, and it matches the, and U delta is 0. Sorry, V delta is supported in a region near the boundary, U delta is 0 on the boundary and nearby. Okay, so I look at U du minus U delta and I try to mimic what we had in the case when the Euler solution was 0 on the boundary. Okay, so I will need the following estimates for the boundary corrector V delta for phi delta and U delta. Here they are. The L infinity norm is O of 1. The L2 norm is O of square root of delta. And the gradient, you lose one more, you lose something and you get O of 1 over delta. You lose, what is it? Delta 3/2. Okay. All right. Now, that's an L infinity. In L2, you only lose 1 over delta. Okay? Okay, so here's a PD for W. W is the difference of U nu minus U delta minus the corrector. Okay, so we have a blue term, which represents a nonlinear term. We have this pressure term here, and the stream function term, and we have the linear term, which is the red term, the Laplacian term. Okay? So I multiply by W, I'm just going to mimic everything, integrate over space, and I get the corresponding terms, blue, green, and red, okay, which I call the blue term is a nonlinear term, the green term is the boundary layer term, and the red term is the linear term, coming from the Laplacian. Okay, so let's work out first the nonlinear term. Here it is, okay. I can rewrite this as U nu times U nu dot grad of V delta minus W times W grad of UE, so that is reminding me of what I had in the simpler case, okay, minus the term near the boundary. So U delta minus UE times U nu dot grad UE minus W times this junk. Okay, so first thing we do is we integrate by parts. The first term, the first integral, I put the U nu dot grad onto U nu times V delta. And I can estimate this by the L2 norm of U nu, which is under control, times the gradient of U nu near the boundary, which is not under control. Okay. The second term I estimate exactly as I did in the first part. Okay. This term here it just gives me a small contribution, delta to the 1/2 times two terms which are under control. And I get another delta to the 1/2 times terms which are under control. Okay, so here's my problem term. That's for the nonlinear term. Next, let's estimate the terms that live in the boundary lane. So here I've got WL2 dt times something which lives near the boundary, but it's bounded null infinity, plus something which times something which is going to be small, plus something which is phi delta infinity, which is bounded. There's a gradient of p on the boundary, which is going to be small. Okay. So I've got two small terms. Okay, and finally, let's look. So this one, the boundary layer term actually has no problems. Okay, it's a small term. Now we look at the linear term. Just integrate by parts using the fact that W is 0 the boundary, and as is U nu, I'm sorry. Okay, so I've got this, and then I split W into gradient of UE and gradient of U delta. Okay. So here we go. And then one of these terms I can throw away. Okay. Finally, I get something which is under control here, because it's got a nu in front, and something which has the worst term, which is gradient of V delta, which is delta to minus 1/2. Okay. So I put all these estimates together, integrate in time. I'm just copying the estimates that we got before, the blue estimates, the green estimate, and the red estimate, and we have these two box terms to worry about. Okay, so first of all, I put all this junk together to show that this all gives me either a ground wall term or a small term. Okay. All right, so what I do here, here's my ground wall term. I just souped the gradient of UE here. I have another small term coming from here. Okay, let's see. Small term, this is doing the same thing. Okay, again, calling attention to the fact that this is a small term here. Okay, and finally, I'm done. So I've got WL2 squared is bounded by my ground wall term, plus some stuff which is small, plus the stuff that's not under control here, which looks kind of similar because this is essentially this term squared, okay, for all practical purposes. All right, hence to show that you have the vanishing viscosity limit holding uniformly in time, I need this to go to 0 and this to go to 0 as delta goes to 0 and nu goes to 0, okay? And now I want to choose a good delta, a decent delta. So the rest of the story is, let me choose delta. I want delta to go to 0 as nu vanishes, so I'm just going to choose delta to be a power of nu. Okay? And if I substitute this, what I want is the maximum between nu to the alpha, just putting delta equal to nu to the alpha here, times the dissipation rate in a region of size nu to the alpha, the maximum between this and nu to the 2 minus alpha, times the same thing to go to 0. Okay. Kato says choose alpha equals 1. In other words, choose the boundary layer thickness exactly of order viscosity. Okay. If you do that, then it becomes a very nice criterion because you get, on the one hand, this implies convergence. You see, when you take alpha equals to 1, you get nu here, and you get exactly nu here as well. U2 minus alpha is going to be nu. It's the same thing. Okay? On the other hand, from the previous step, okay, we already had that convergence implies that nu times the dissipation rate on the whole domain vanishes. Okay, and therefore, you get an if and only if criterion. Okay? Of corollary of the Kato criterion is that, in fact, if you choose any alpha between 0 and 1, and this goes to 0, then u nu goes to 0, then the vanishing viscosity limit holds. And if alpha is greater than 1, then you can choose nu to the 2 minus alpha times this going to 0 also implies convergence. In other words, in a sense, there's nothing special about this boundary layer of thickness nu, except that it gives you an if and only if criterion. Okay? That's the only thing special. But if you properly balance by putting a proper weight in front of the dissipation rate, you can have dissipation on regions of thickness greater or less than nu, and have the vanishing viscosity limit hold. All right, let me discuss some comments and extensions of the Kato criterion. First of all, the same result holds in 3D, and it's a similar proof. You substitute the energy method by the energy inequality because you can't simply multiply by W and integrate. 1998, Calmon and Wang substitute the sufficiency condition for a condition on the tangential pressure gradient. In 2001, Xiaoming Wang showed that, in fact, you don't have to have the full gradient vanishing in a region near the boundary. It's enough that the tangential gradient vanish. And what I find the most interesting extension is to substitute the Kato criterion with a vorticity instead of the full gradient. This was done by Jim Kelleher in 2007. Okay, and it's also an if and only if criterion. Okay, and in a very recent paper that still has not come out, but there's a preprint this year. It's also preprint by Jim Kelleher this year as well. Peter Konstantin, Igor Kukalvika, and Vlad Vickel showed that there's a criterion for convergence whose proof is very much in the spirit of Kato, okay, holds, which includes and extends the Oleinik condition on the no backflow, okay? And it also, so the Helena condition on no backflow is a criterion for the well-posedness of the Prandtl equations. There is a very close correlation between the Prandtl condition, the Prandtl equations being well-posed, and the vanishing viscosity limit holding, but this has never been actually explored sufficiently in the literature. So this is sort of a first instance in which this is being explored. Okay. Now, I want to discuss further applications of these boundary correctors and energy methods for vanishing viscosity and associated singular limit problems holding. Okay, so one is if we look at the small hole and small viscosity limit. Okay, so this joint work with Rago-Shiftimi and Milton Lopes, 2008. And the idea is I'm going to look for a solution of the Navier-Stokes equations in a domain which I call pi delta, which is a domain exterior to a small hole of size delta. So take a small hole of diameter delta, okay? And I'm going to make this hole shrink. I'm going to make delta go to 0. And I want to know what happens in the limit as I take both the viscosity and the size of the hole to 0. Okay, 2D or 3. Okay, so if UE represents again the Euler solution, which lives on some time interval. At 2D, of course, this time interval is going to be infinite. In 3D, it's possibly finite. If the initial condition for, now at this point, I'm not allowed to take the same initial conditions, okay, irrespective of a initial layer, because in an exterior domain flow, you need the initial flow to be at least tangent to the boundary. The boundary is there at level delta, even though it's not there when delta is 0. Okay, so I'm not allowed to take u naught delta equal to u naught. All right, but I suppose that u naught delta converges to u naught in L2 when delta goes to 0, and then I can find a constant such that if delta is sufficiently small, namely less than order nu, then the Navier-Stokes solutions outside a small hole tend to the Euler solution as delta goes to 0. So delta and nu going to 0. Okay? So this is a coupled limit here. And the proof is very closely related to the proof of the Kato criterion. Okay. The key difference here is that our boundary corrector has a gradient which is actually of order 1. Okay, so differently. So in the Kato criterion, the general boundary corrector had a gradient which was ordered delta to the minus 1/2. That's how come you got a criterion, and in this case you actually get a theorem. Okay. Another situation in which we looked at was the expanding domain and vanishing viscosity. So here I'm going to be solving this joint work with Jim Kelleher and Milton Lopes from 2009. And here I'm going to be looking at Navier-Stokes in a really large ball or a really large domain. Doesn't matter. I'm going to scale this domain with R. Okay? And at the same time, I want to send viscosity to 0 and send the domain to full space. Okay? Again, 2D or 3D. So the notation is that U nu R represents the Navier-Stokes solutions in the domain omega R, okay, with viscosity nu, and initial data U naught R. UE is the Euler solution, which lives on some time interval 0t, tb infinity in the case of 2D. Okay? Again, I'm going to suppose that U naught R converges to U naught as R goes to infinity. And then the theorem is that for any R going to infinity as nu going to 0, irrespective of rate of going to infinity, U nu R converges to U Euler when nu goes to 0. Okay, so you get the vanishing viscosity limit holding at any rate that the domain is expanding out to infinity. Again, the proof is very closely related to the proof of the Kato criterion, and in this case, the key difference is that the gradient of the boundary corrector actually goes to 0 when R goes to infinity. And that is how come we can take any R of nu going to infinity at any rate, doesn't matter. Okay? Because in this case, it vanishes. Okay, so next I want to address what are some of the difficulties in the vanishing viscosity problem. Question 1, is the linear term responsible for this problem being difficult? So let's consider a flow in 2D in a disk with radially symmetric vorticity. That will take care of the nonlinear term, not present anymore, just the linear term, and let's see if that's the problem. That's the issue. So Navier-Stokes becomes Stokes, okay? And in this case, we can prove that the Navier-Stokes solutions converge to the Euler solution as the viscosity vanishes, okay? Because the Euler solution is steady. Okay, so this is actually just a heat equation in the end for the vorticity. That's what you're doing. So we play with semigroups here. Okay? This is joint work with Anna Matsukado and Michael Taylor. I forgot to mention this. This was shown first by Matsui for smooth data, non-compatible boundary conditions initially, and Bonawu, well, I've already discussed their work, and then we actually rotate the boundary with Anna Matsukado and Michael Taylor, so we'd rotate the boundary at a rate which is of boundary variation, alpha of t, BV. Okay, so that's Matsukado and Milton and myself in 2008, and Matsukado, Milton, myself, and Michael Taylor in 2008 as well. Okay? So, next, is the issue, at this point we've decided that the problem is not just the linear term. It's not the main issue. Okay? So maybe it's the non-compatible boundary conditions, the mismatched boundary conditions, the fact that you have no slip in one case and slip in the other, or the nonlinear term. All right, so let's do the following. Let's change PD, keep the mismatch, keep the nonlinear term, and let's see if we arrive at the same kind of difficulty there. So I'm going to look at the Euler alpha equations. So the Euler alpha equations are this system here. So I have dv dt plus u dot grad v plus sum of Vj grad Uj is minus the gradient of pressure. Divergence U is 0, and V is the identity minus alpha squared Laplacian applied to U. So it's the Helmholtz operator applied to U. Okay? Plus boundary conditions on the boundary. All right. This is a regularization of the Euler equations. If you want, this is V flowing by U. U is 2 derivatives better than V. Okay, so use a regularization of V. Okay, by the way, the Euler alpha equation arises as the inviscid case of a second-grade fluid model, which is a model for non-Newtonian flow. It's not a model that's taken very seriously in fluid mechanics, but nevertheless, it does have a strain matrix and a tensor, a stress tensor, sorry. Okay? So this was introduced by Dunn and Fosdick in 1972, and it's one among a hierarchy of differential type non-Newtonian models. It also corresponds to the inviscid Kamasa-Holm equations, and it's also, this is very interesting, actually it also arises as the geodesic flow on the volume-preserving diffeomorphism group with the induced H1 alpha metric. Okay? This was shown by Jerry Marsden, Tudor Rachu, and Steve Scholar in 2000. The H1 alpha metric is simply the H1 norm, if you want, with a weight, alpha squared. Now, the Euler alpha equations do not come with natural boundary conditions, okay? But since they do correspond to an actual fluid mechanics model, which is the second grade fluid model, which is actually coming from physics, and since in that case, it's natural to assume no slip, why not just set it to be no slip when you have zero viscosity, the inviscid case as well? Okay, so that's what we're going to do. We're going to assume no slip. Okay, notice that this PDE is third order. Okay, you have here, for U, you have the gradient of V appearing here, so that's what you have is the gradient of the Laplacian of U, so it's the third order PDE, okay, in space. So it allows for setting U equals 0 on the boundary. It's a valid boundary condition. And the question that we ask is, as alpha goes to 0, does this converge back to Euler? Again, I'm taking non-penetration for Euler and no slip for Euler alpha. So it's exactly the situation in which I have a non-compatible boundary conditions and a nonlinearity, similar nonlinearity to Euler. Okay? All right. If U naught alpha is an H3, I would need at least 3 derivatives here, and H1 0, and is divergence free, then there's a well-posed result. There always exists a unique solution of the Euler alpha equations, which is global in time. This is 2D, and this was proved way back in 1994 by Choranescu and Choucault, extended by Boussac in 1999. And there's another proof, a geometric proof by Marsden, Rachu, and Scholar in 2000. Okay. 2D a priori estimates that we have are the following. The solution U alpha satisfies this energy balance. So the energy balance is this natural H1 alpha norm. Okay. Of course, if alpha goes to 0, you lose all estimates on the gradient. Okay. The curl is the curl of V alpha, or the V's. The curl of V is transported just like in the Euler equation, 2D Euler equation for vorticity. Okay, so you get the L2 norm is conserved. Okay, and if I now take an H3 initial data, which is divergence-free and only tangent to the boundary, I'm going to introduce what we call a suitable approximation to this initial data, which is a sequence of functions or vector fields that vanish on the boundary, that converge in L2 to this initial data, this non-penetration initial data U naught, whose gradient is little o of 1 over alpha. So notice that the gradient in L2, it blows up, but it blows up in a controlled way. It only is initial data. Okay, and in H3, it blows up like 1 over alpha cubed. All right, so I'm going to call this a suitable family of approximations. And we show that for any initial data in H3, which is non-penetration and divergence-free, you can always construct a suitable approximation family associated to this U naught. Okay? So for suitable approximations, we get the following a priori estimates for U alpha time t. Now these are uniform in time, so give this estimate here that the gradient in L2 is little o of 1 over alpha becomes gradient of U alpha time t is bounded by 1 over alpha, and this condition here is also preserved. U alpha in H3 is also like 1 over alpha cubed. Okay, so with this setup, we have the following result for the vanishing alpha limit. This is joint work with Milton, Idris Titi, and our postdoc Ibn Zhang. Fix t greater than 0, and U naught in H3, div-free, non-penetrating, tangent to the boundary. Take a suitable family of approximations in H3, okay, and look at the associated solutions to Euler alpha with this initial data. Okay. Look at the Euler solution corresponding to U naught. It's going to be continuous in time in H3, C1 in time in H2. Okay. Then not only the vanishing alpha limit holds, but you even have a good estimate of the the alpha squared gradient of U alpha L2 squared term. It goes to 0 uniformly in time. Okay, so very different situation from the dissipation rate in Navier-Stokes. Okay. The proof follows along the Cotter criterion. In fact, the story of this proof is very funny because we could have sworn that this wasn't going to be true. Okay. We decided to look at this problem by, motivated by looking for another instance where you had something like the Cotter criterion, and let's figure out what the criterion is going to be. Okay. And we started fooling around with the estimates, and lo and behold, there's no criterion. You actually do have convergence. Okay. So this is what we were rather surprised with this. So you look at W, which is a difference, write an equation for W, multiply by W, integrate space and time, use the Cotter boundary corrector, and you end up with an estimate like this. Okay. The point here is that all the terms end up having an alpha in front of them. So you have things like alpha times delta to the minus 1/2, that's the worst term, and alpha squared over delta over here. Okay. So all you have to do is to choose delta equals to alpha. Okay. And, oops, Nussenzveig is not here to give the talk tomorrow. This is a recycling of old slides. Sorry about that. All right. Okay, so what's the upshot? So for Euler alpha no slip, you have convergence to Euler, even with mismatched boundary conditions, and a nonlinearity present. Okay. What have we learned? The difficulty is therefore not simply the mismatched boundary conditions. It's not in the linear term because we removed the nonlinearity and we still had convergence. It's not due only to the nonlinearity, in other words. Or is it? Okay. In fact, both the Euler and the Navier-Stokes equations have a very special nonlinearity, which is not the same as a nonlinearity. It's almost the same. It's very similar to the nonlinearity from Euler alpha, but it's not the same. What's special about it? If you look at shear flow, i.e. vortex sheet type of flow, okay, the Euler, and you put this into the Euler nonlinearity, you do the linear stability analysis, and you see that the higher modes have an exponential in time growth. And that's known as the Kelvin-Helmholtz instability. If you do the same calculation for Euler alpha, again, with vortex sheets, you do the linear stability analysis, you have controlled growth of the higher modes. Okay? So Euler alpha is not subject to Kelvin-Helmholtz instability. The vortex sheet problem for Euler alpha is well posed in time. In other words, the Birkhoff-Rod alpha problem, for those who don't know, is well posed. This was proved by Claude Bardoche, Jasmine Lynchitz, and Idriss Titi in a series of papers in 2008 and 2009. Okay? So what does this have to do with vanishing viscosity and mismatched boundary conditions? These mismatched boundary conditions lead naturally to a vortex sheet on the boundary. Okay? It leads to a lot of shear on the boundary because you have on the boundary you have, for Navier-Stokes, you have the flow adhering, the particle fluids adhering to the boundary, but for Euler they're just slipping by. Okay, so that you have a thin region with an intense shear or a high gradient, in other words. Okay, so that's typical of vortex sheets situation. So this is why the absence of Kelvin-Helmholtz instability for the Euler alpha equations is relevant in this problem. So and as far as I can understand it, the main difficulty in the vanishing viscosity limit is the Kelvin-Helmholtz instability. How do you control that? Okay, so in at least one instance, you have absence of Kelvin-Helmholtz instability leading to convergence. The Cotter criterion, therefore, can be understood as a way to rule out, to exclude Kelvin-Helmholtz instability near the boundary, i.e. the creation of small scales at the boundary. That's what you're doing when you satisfy the Cotter criterion. Okay? Another observation that I think is noteworthy is that the Cotter criterion, the proof, assumes that the Euler solution is smooth. all of the estimates that I did, I said, oh, the U Euler, that's under control. Okay, the gradient is L infinity. I don't have to worry about that. And then the question is that a reasonable assumption? Okay. So I claim that the vanishing viscosity limit problem should actually be studied for Euler solutions which are not smooth, that have vortex sheet regularity. And in 2D, this problem is still not closed. It's still open whether you can, in any sense, have an evolution, a well-posed evolution with vortex sheet initial data for the Euler equations. Okay? You know that to be true when the vorticity is under control, for instance, when the vorticity has a distinguished sign, but otherwise it's still open. And while it's still open, the vanishing viscosity limit problem will also still be open. Okay, that's the moral of my lecture. Okay? All right. And as far as the thickness of the Kato boundary layer, what we've learned is that it's not all that meaningful, although there's still some kind of miracle that the thickness exactly size due is enough for an equivalence criterion. And I'm done.